So I would like to report on some recent work with Jeff Galkowski from University College London, and it's about Keldish operators or generalized Keldish operators. So a Keldish operator is an operator of the following form, where it looks like a Laplacian, except that we multiply the first second derivative by x1, and there may be some lower order terms. In the simplest case, it would just be a constant times dx1. And the generalized version is an operator which is of this form, but we now allow non-constant coefficients in front of, say, lower order term, and we allow the Laplacian, if you like, in the second variables is replaced by an elliptic operator with a real principal symbol. And the assumption in this talk is that this symbol, this operator here, is real analytic. That is to say, the coefficients are real analytic. And I will actually consider more general operators yet. And operators of this kind are relevant in various places. So I just mentioned a few things here. My interest in them comes from the work of Vashi, because they appear in both scattering on asymptotic hyperbolic spaces, but also in general relativity. And the theorem that we proved with Jeff Galkowski says the following thing, that suppose U is a solution to the equation, P equals F, and in a neighborhood of 0, U is smooth, and PU, the right-hand side, is analytic in a neighborhood of 0. Then U is analytic in a neighborhood of 0. And actually this follows, as I will explain, from a theorem for more general operators and from a microlocal rather than only a local statement. So why study such a thing? Why would I be interested in this? Well, let me just give one motivation coming from general relativity. When you look at stationary black holes, so in that case, the space-time, say, is given by time cross some interval where RC could be finite or infinite, and then cross with S2 with some D'Alembertian corresponding to the metric. So I won't give all the details or write down some complicated formula here. This R plus is the event horizon. So if you like, this is the place, the boundary of the black hole. RC is the cosmological horizon. And so I have trouble drawing Penrose diagrams. So Peter Hinz drew Penrose diagrams for me for this talk. And in the case when you have positive cosmological constant, the resonance states or quasi-normal modes for such a black hole are smooth solutions to the equation D'Alembertian, then some exponential with some suitably rescaled or re-normalized time times uj, which does not depend on time. So in other words, the fact of being a resonance state on quasi-normal modes in this setting corresponds simply to smoothness across these two horizons. And the idea is that, you start with some smooth or analytic data, and well, actually it doesn't matter, smooth data, say smooth compactly supported data, you get a smooth solution, and that solution has an expansion in terms of this mode. That's a definition of that's the statement about the relevance of these quasi-normal modes. And it's sort of a natural question to ask whether these modes, which are C infinity, that's sort of the way that one can define them, are in fact analytic across these surfaces, the event horizon and the cosmological horizon. Partly because, when you have analyticity, you have all sorts of nicer continuation properties. And also what happens is that, you know, smooth functions that are not analytic actually are fairly rare in nature. And so if indeed they would say appear in this situation, it would be interesting. In the case when the cosmological constant is, sorry? Sorry? Oh.
No, please go ahead.
Okay. So in the case when the cosmological constant is 0, well, it's a more complicated situation near the cosmological horizon. There some outgoing condition is needed, so it's not quite as simple. But near the event horizon, the black hole, the issue of this analyticity is the same as in the cosmological constant equals to 0 case. So I won't write down equations, you know, corresponding to the operators here, but I'll write the operator that Vashi used in the asymptotically hyperbolic scattering. And that is of the form that I described before. You see, you have x1 times dx1 squared. So my d has always an I in front of it. So d, this is a non-negative operator, minus this term here, and then some Laplacian respect to some metric depending on x1, plus some other terms. And the resonant states for hyperbolic, asymptotic hyperbolic scattering are characterized by demanding that we have solutions of this equation P of lambda u equals 0, so it's sort of a non-linear eigenvalue problem in lambda, which are smooth across x1 equals to 0. And again, the question is, are they analytic? And even you know, so then under analyticity assumptions on metric, for instance, even for constant curvature spaces, this analyticity of this resonance state implies analyticity of radiation fields and so on, which actually wasn't known even in constant curvature, which is really strange. So motivated by this, actually in a survey paper a few years ago, I made a conjecture, because I didn't know how to do this, is that if U is smooth, then and P of lambda U is analytic, well, in the case of resonance states just 0, then U is also analytic. So that's a, sort of a statement that, is the spirit of old microlocal analysis. And actually, I just want to say, I won't list them, but just to encourage people in the survey article, easily found, there remain 3 2-star conjectures and 5 3-star conjectures. So the price for the solving a conjecture is a dinner in a 2-star restaurant or a 3-star restaurant. I had a feeling that this was somehow possibly doable to people who knew more about this subject than I, and that's why I gave it a 2-star. And so far, it's the only conjecture that was solved. So there were some previous results actually with Gilles Lebord, sort of small time. We just to look at it, we considered the case where H is independent of X1 and this term is not there. So a case in which you can separate variables. And indeed, in that case, this is true. So this is not, of course, meriting any prizes for lambda, which is not in some set of special values. But actually, Claude Zully proved the conjecture for any lambda, which is again not in this special set. And we did have a 2-star celebration. And I have to say the restaurant promptly lost a star. So I don't know what sign it is about the future of my conjectures. And the proof relies on earlier results, old results from the 80s and 70s by Bałędy, Kulawik, Bolle-Camus, Anouzet. And they relied on even older methods. So, but they were not microlocal at all. I mean, the proofs, in fact. So before actually, so what I wanted, first of all, I wanted a proof that I would understand, because these are long and complicated papers. So, and Claude Zully wrote a nice description of the first of all reduction to those papers, and then describe the ideas behind the papers, and also I was surprised by this condition here. That condition came from more or less from these works, and it had something to do with solving the non-homogeneous problem with an analytic right-hand side, finding an analytic solution, then working with a homogeneous problem. So before going into more details, let me make a few comments about analytic hyperlipticity. So this is an old subject. First of all, these operators, Keldish operators, are not C-infinity hyperelliptic. You know, if PU is smooth, then U does not need to be smooth. Well, it's kind of, in general, not, I mean, it's pretty obvious, I would say, because, you know, one of the features here is that when x1 is negative, this operator becomes hyperbolic. When x1 is positive, it is elliptic. So you would not expect this type of statement. And in fact, you can take some simple example like this, for which PU is equal to 0, and obviously U is not smooth. So on the other hand, in the opposite direction, the study of operators that are C-infinity hyperelliptic, but not analytically hyperelliptic, that is to say, PU smooth implies U smooth, but PU analytic does not imply U is analytic, has a long tradition with connections to several context variables. So my colleague Mike Christ worked a lot on that, but some of these works continue, for instance, in the Bologna school. And the simplest example from Hermander's book is this operator that has this property that it is not infinity. It's infinity hyperelliptic, but not analytic hyperelliptic. Now, some operators which sort of Fuchsian operators, degenerate operators. So this is not a Fuchsian operator, but it is degenerate. They are typically not hyperelliptic, but we can have the property like the one that's in our theorem, that U smooth, PU analytic implies U is analytic. So for instance, the works used by Zulli are of that type. And another class was considered by Bawendi and Shestrand a long time ago, but I would recommend this paper for reading. It's I would say, the easiest paper to read by Johannes in my experience, and that concerns generalization of an operator of this form, and the key role there is played by the indicial operator. This is sort of a B operator in the modern parlance, and the properties of this operator play a role. And actually, one could ask if there are generalizations to more geometric classes of operators of this kind of results. Another comment is about the Tricomi operator. So, you know, the other operator, the other sort of model, standard operator, where you have a change from hyperbolic to elliptic, is the operator which is given as follows. You have x1 in front of dx2 squared, and this operator again changes its behavior from elliptic when x1 is positive to hyperbolic when x1 is negative. And this operator is sort of better known than the Vashy operator. So this result is false for the Tricomi operator. The Tricomi operator does not have the property that when PU is analytic and U is smooth, U is analytic. Well, so this can actually, one can construct a simple example using Airy functions and so on, but I would like to move on to sort of a microlocal point of view and draw the characteristic varieties for both Keldish operator and Tricomi operator. So Tricomi operator has x1 here, Keldish operator has x1 here. And what I'm drawing here is the a cylinder which corresponds to the values of the circle are the values of psi1 and psi2, the psi variable, you know, the cotangent bundle at infinity. So cosine theta, theta is this circle here. That is just the projection to infinity of psi1 and psi2. And x1 is this line here. So the cylinder, the surface of the cylinder is infinity in psi and the direction of x1. And what happens is that the characteristic variety is given by this. Let's just, you know, replace this by psi1 square, psi2 square, and then take psi out, and that's what we have. So they actually look the same. They're sort of parabolae on the surface of the cylinder. However, the behavior is very different because here in the Tricomi case, you have nice, by characteristic, these curves are completely non-degenerate. I mean, the Hamilton vector field is completely non-degenerate. On the other hand, in the Keldish case, there are radial points here on the circle. So consequently, you know, you sort of see that you can have propagation here. So just results about propagation of analytic singularities would show that you cannot have this type of property that I was, PU analytic, U smooth implies that U is analytic. Oh, sorry, propagation of singularities. Because you, but here we have radial points. So radial points means that the Hamilton vector field of this operator is proportional to the radial direction xi dot d xi, or in other words, if I would look at the Hamilton vector field on this after this rescaling, the Hamilton vector field has a projected to this boundary of this cylinder, has fixed points here. So this leads to a set of general geometric assumptions. We now look at an operator which generalizes, eventually generalizes this, but this is the picture in this special case. This is a lower order term. The symbol, principal symbol is given by this. The Hamilton vector field is given by that. And as I said, when x1 is equal to 0 and psi2 is equal to 0, that's on the characteristic variety, the vector field is proportional to psi1 d psi. And the radial sets, the sets where we have this property, are radial Lagrangian. Well, they're Lagrangian submanifolds, so characteristic Lagrangians, which are also radial in the sense that this vector field, the Hamilton vector field is equal to a radial vector, parallel to the radial vector field. And actually in that setting, a useful tool are the radial estimates, sort of microlocal propagation estimates, which came from scattering theory. And in a way, Melrose distilled the sort of scattering outgoing estimates to sort of a microlocal statement, and those are those radial estimates. And they've been very useful, in particular in the work of Vashi, and also in my work with Dyatlov, because in our case, the previous works, Melrose, Vashi, the radial sets were always some kind of Lagrangian or smooth sets, but in many situations they are very rough sets and they're not really radial. But those results are sort of robust enough to handle that. And recently there's some improvements at the endpoint with Besso-Western by Wong. And actually they're also related to something called the redshift estimates. They are in a way a microlocal version of the redshift estimates in general relativity. So what are the general, I should say, actually there's another, and those, so what are the uses of this radial estimates? One uses the following, that if I have, say, let's just say this operator here, then if there exists some threshold S naught, so that if PU is smooth and U is in Sobolev space a little better than this S naught, then U is actually smooth. So for example, here, this S naught is imaginary part of A plus 1/2 if I got the sign right. Okay, so the general geometric assumptions will follow papers by Haber and Vashi, except for throwing in analyticity. So now we take an operator of arbitrary order. This is an operator of arbitrary order with analytic coefficients. And the principal symbol is given by this. And the assumptions are that the principal symbol is real valued and that there exists a conic Lagrangian submanifold on which dp does not vanish, but the Hamilton vector field restricted to the Lagrangian submanifold is parallel to the radial vector field. So this is exactly the situation that we have for generalized Keldish operators. And now we have a result which is kind of, result from the 80s or whenever, that, that if a point on this Lagrangian is not in the wavefront set of U, and it is not in the analytic wavefront set of PU, then it is not in the analytic wavefront set of U. So this is a microlocal version of the statement before. So now, the nice thing is now everything is microlocal, and also, it's in this general setting. So for this operator, for the generalized Keldish operator, what we had was that this was elliptic and real in dx prime. And in that case, this radial Lagrangians are given, just like in the model case, are given by this Lagrangians here. Analytic regularity, just elliptic regularity, shows that if I'm at x1 equals to 0, then x1 equals to 0, then the wavefront, analytic wavefront set has to be contained inside of psi prime equals to 0, but when x1 is equal to 0, this term disappears. And then if this term is elliptic, then we would have regularity. But then if U is smooth, then the theorem, well, then there's no wavefront set at all. Then the theorem shows that the wavefront set of U is intersected with this set, is empty. And then U is analytic, because that's where the only possibility that the wavefront set. So hence U is smooth, smooth, and PU analytic implies U is analytic. So that's that, but it's nice to have this statement. So here no ellipticity assumptions are made. It's just this geometric assumption. So this is of course a local result near x1 equals to 0. So let me actually give a proof of this in a simplified case, but very simplified case. So please don't laugh. I will prove it in this case. X dx plus a. Actually, this proof with just modular manipulations would apply to some cases where I have some sort of Keldish operator. But let me give a complete proof in this case. But also under some stronger assumptions, just again to be able to write it down on one page. So I will assume that PU is equal to F. U is a Schwartz function, so that's a sort of global statement about smoothness, and make a stronger assumption about analyticity. Rather than say that F is analytic, I'll make a stronger statement that e to the power x, absolute value of psi, f hat is in L2. That implies analyticity. It's sort of a quantitative statement of analyticity. And well, that's what I said, F is analytic in that case. So to prove, so now we would like to prove that U is analytic. With, of course, in this case, one can prove it by all sorts of methods that don't require any analysis, but let's prove it using methods which generalize. So for that, I introduce the following function, which is a function which is logarithmically bounded, depending on epsilon, but as epsilon goes to 0, it becomes closer and closer to psi, absolute value of psi. So this is how this function looks like as epsilon changes. I mean, this is really silly, but you know, it's just a function which is like a log at infinity, but up to 1 over epsilon, it's like absolute value of psi. So as epsilon goes to 0, it becomes like absolute value of psi. And then we use this G epsilon to build a multiplier, Fourier multiplier, and we exponentiate it. So this, or if you like, this is just a Fourier multiplier. And we define these two functions. So note that U is smooth, U is Schwartz. So this is polynomially bounded because of this bound here. So this actually is bounded in L2, and this is bounded in L2 uniformly with respect to epsilon because of this condition. So what we have is that U epsilon is bounded in L2 in a way depending on epsilon, and F epsilon is bounded in L2 independently of epsilon. And then we follow again a long tradition, and we conjugate this operator by this weight. And well, in this particular case, everything is very simple because there's no X dependence here. There's just a Fourier multiplier. So the only conjugation, the non-trivial conjugation through X1. But conjugation through X1 gives me this term here. So now we need to differentiate this function G with respect to psi and see what properties it has. And the property that it has is that if I take psi sufficiently large and epsilon sufficiently small, then psi G prime psi is bounded from below by a constant, which can be arbitrarily large if I take this case like that. And the reason that I want this to be arbitrarily large is that I want to control any lower order terms. Of course, in this case, it's a very simple lower order term, but you know, if it's complex, we have trouble. And now we do the usual type of estimate. We look at the imaginary part of P epsilon, U epsilon. Well, that of course is bounded from above by F epsilon and U epsilon, and that by Plancher's theorem is U epsilon hat. And that is just equal to this. That's just the imaginary part of this thing here. It's given by this. And on the Fourier transform side is this. But now, if psi is sufficiently large, this is bounded from below by any number. So in particular, I can make it larger than this. And that gives me this. And then I have something left from psi less than or equal to minus m. But that is bounded by, say, H1 norm of U, which is fine because U is in Schwartz. So the final conclusion is that U epsilon hat is bounded by F epsilon in norm plus some constant which depends on U, but is bounded uniformly with respect to epsilon. And that proves this, that e to the power psi U hat for psi non-negative is bounded. And then similar argument for psi negative guarantees that e to the absolute value of psi U hat is bounded, and hence U is analytic. Okay. So this is the idea of the proof, namely you construct a suitable weight, and then you want to understand some positivity properties. So, you know, I won't go into so technicalities of it in the general case, but let me just give some indications. So the first indication is that, you know, constructing G epsilon by hand for even the Keldish operator, not the Keldish operator, that I did it, but for the Keldish operator, the generalized Keldish operator with non-constant coefficients is tricky because of various localization issues to obtain a G epsilon which has sufficient good properties, sort of analogous to this property. But actually, it is easy because we can use a normal form theorem of Haber, and that's based on earlier works of Guillemin and Schaefer on Fuchsian operators, and that was based in turn on the proof of Sternberg's linearization theorem by Nelson, and that makes life much easier. And of course, these normal forms are in the C, even though operator is analytic, the normal forms can only be achieved in the C infinity category, but these weights only need to be C infinity. So consequently, we don't need to rely on analyticity here. And that's actually, I must say, I was sort of studying this theorem because of that. And I remembered the work of Haber, and that really saved a lot of work because you basically can construct G epsilon in the model case, and all the localization things you can control, and you know that the Hamilton vector field will not affect them, etc., etc. And that's a remarkable theorem, actually. And then, of course, you want to implement it analytically, and that's based on complex microlocal deformations. And in a way, they were already mentioned in the early morning and for me late night talk by Johannes Sjöstrand. And in our context, they go back to methods of Elfer Sjöstrand and Sjöstrand from, oh gosh, almost 40 years ago, no, not quite, 35 years ago and 25 years ago. And those works were motivated by the study of quantum resonances, and they followed, among other things, the works on asymptotics of Bergman kernels that we heard about yesterday. Today. And another approach to weights is also due to Nakamura, Martinez, and of course many other works. But our main motivation or source was this paper. And they were revisited, this method were revisited to the case in which was needed here by Jeff Galkowski and myself for other reasons, and for completely different reasons, by Geddes, Bontenot, and Jezequel. And they gave extensions which sort of morally already were there, but it was not explicitly available, to the case of G epsilons, which are in S1. So you see, if one goes back, so I shouldn't really do this, if one goes back to my G epsilon here, then of course this function here is logarithmically bounded, but in a way depending on epsilon. If we want uniform estimates on G epsilon, then it is in S1, in fact, so it behaves like psi. And hence, you know, if I want to implement sort of conjugations like this, one needs to know this theory in the setting of weights which are in S1, and also in some cases on manifolds. So in my last few minutes, I rather than you know explain the technical things because there's no time, I will just say a few words about other applications.
Sorry, Maciej, so you're already off by 4 minutes. So
I'm already
right. So
oh, I see. So let me just show a movie. Oh,
yes.
Sorry about that. I got confused about time. Yes. In any case, I paper with Galkowski, we proved a certain result which shows that the limits of the spectrum of an operator to which some viscosity term was added converge to some fixed set in a setting motivated by some fluid dynamics problems. And Geddes, Bontenot, Jezequel, a completely different setting, gave a microlocal proof of the order of order as a meromorphic function of the Ruel zeta function for analytic Anosov flows. And maybe I should just say that they actually provided a microlocal proof of, well, Fried's estimate on the order, but also they provided a sort of interpolated order estimate when the flow is not analytic, but Gevrey. Okay, so on this cheerful Gevrey note, I finished. Sorry to be late. I had to go over time. For some reason, I got confused about the time.
So thank you very much for very interesting talks. Are there questions or remarks?
I have one question about, but maybe it's only your complete proof of the simplified case took my attention. It's about how this simplified case suggests the construction of these weights to the general case. Maybe it's I'm a PhD student, and this is maybe interesting for me. Oh, this is a nice idea. Why?
Okay, well, thank you. Yes, no, it's but that's often how it works in this business. And in fact, this is the strength of the microlocal methods, because you know, we know how it's all connected to symplectic structure. So if one can find normal forms, which actually Haber's normal form is this operator, you see, microlocal. He actually has a stronger result, but the only thing I should stress that the normal forms are in this infinity category. So you could not somehow, you know, use the normal form to prove the theorem, but you can use the normal form to construct the weight. And the trickiest thing in this construction of the weight, at least me, is here you don't, you know, it's one dimension, but in higher dimensions in these microlocal states, we need to localize things, and you need to make sure that the Hamilton vector field falling on the localization pieces is not going to cause any trouble. And here the normal form is extremely useful. And it's highly non-trivial because the Sternberg linearization theorem is highly non-trivial. At least to me, I mean, but I think to everybody.
Thank you very much.
Further questions? So I have one, Maciej. So because it was attracting my attention, this XDX operator, of course, you know, but suppose that you take another vector field, say you take a sum x1 dx1 plus x2 dx2, and then you form a different kind of Keldish operator, whatever, no longer Keldish, you call it whatever you wish. But so then, of course, the normal form changes and also geometry changes. But do you have the feeling that maybe something could be saved?
Well, no, but I mean, some of those operators, like the operator that you mentioned, I mean, they would still satisfy this hypothesis.
Yeah, it's a radial operator in a sense.
Yes. So you know, I haven't. You know, my motivation came from a very concrete question in scattering theory. So I haven't really considered more general operators. The only reason that we formulated the result using this Lagrangians and so on is simply that, you know, it's just a neater statement, and you really know what is the essential part that you are using. But, you know, my motivation is all from the operators arising either in this general relativity case or in the case of hyperbolic, asymptotic hyperbolic scattering.
Yeah, but because I was thinking about this kind of family of vector fields that have a critical points for which you still have a hypoellipticity or no longer have hypoellipticity. That's so it was curious to me. Well, okay, so if there are no further questions, I wish to thank again Maciej Zworski for his very interesting talk.